So in a live coding session the other day, I mentioned that using ASTs to generate code in a genetic programming algorithm experiment could help me converge on a solution faster. But what is an AST anyway? Well, it's an abstract syntax tree, and it took my college professor something like 2 or 3 weeks to explain how ASTs work and how compilers use them. So I'm gonna try to explain it in 5 minutes. Yes, we're going to use stuff that other people have made. To explore how computers use ASTs to understand your code, we're going to use 2 open source projects. The first is Prettier, which is a thing. I don't actually know what it would be called. Basically, Prettier is a thing that takes your code, parses it into an AST, removes any useless things from the AST, and then uses that abstract syntax tree to output pretty code back. And Babylon is the JavaScript parser that both Prettier and Babel and probably others use. Over here, I've prepared a little test harness that will let us generate ASTs and see what they look like. We import Babylon, Prettier, and Node util. Then we have our code. This is the stuff we're going to be parsing. And we use babylon.parse of our code to get the AST, and then we print it out, making sure to use util.inspect with basically telling it to print everything. Now, if I run this code, it should be able to tell me what is the AST for this essentially empty line of code. And the way it looks is it starts with a node called file, which contains a program with a single node called program. That one doesn't have a body, but it starts with at position of line 1, column 0, and ends at line 2, column 0. Essentially, what this AST means is that we have one line of code. Now let's see what happens when we add a simple variable declaration. A becomes 5. And when we run that, we get a much bigger AST. A much bigger AST. Right, so we still have our file node from before and our program node from before. What's new is all this body stuff inside the program. We have a top node called variable declaration, which then has a child node called variable declarator. That one has an ID with an identifier node and an init node that calculates the value. In a picture that looks a bit like this. You have a declaration node which holds a list of different declarators, and then each declarator has an ID node which calculates the name of the new variable, and an init node which calculates the value. Both ID and init could be potential larger trees that have more calculations and more nodes in them, but that would get very difficult to explain and to show you. The main thing I wanted to show you was that an AST tells you what the code does, not what it is. So basically we have variable declarations, variable declarators, inits, identifiers, stuff like that. What we don't have are tokens, because tokens come in a different part of it's the AST object, but it's not considered part of the abstract syntax tree. That's where you have things like a token for let, a token then for a name. A name can be literally pretty much any string. Then you have a token for the equal sign, a separate token for the number we used, even a token for the semicolon, and a token for the end of file. Now, I don't know exactly how the Babylon parser works, but the way parsers usually work is that you have something called a tokenizer that goes through the file, turns it into a list of tokens. Then the parser walks through the entire list of tokens, and for each token sees, okay, for this token I have to start a new expression, and it starts a new node. Then it reads the next token, this one is a name, and it also starts a new expression, and it adds it to the previous node as a child, and then goes from there. It's really rather complicated. I remember implementing a compiler in college, and it was basically a semester-long project, and in the end we got a very, very simple language kind of working, and the final exam was add this feature to the language. It was probably one of the most fun courses I've ever had, but it was also really, really hard. And that's the gist of how ASTs work. I'm not sure when you're ever going to use this knowledge, but I feel like every programmer should have a rough grasp of how computers understand their code. Now before I go, I want to show you one more thing. How Prettier uses ASTs to do something completely awesome. Look at what I'm doing to this code. So I throw it through the Prettier formatter and it creates this. Let a equals 5 out of code that looks like this. And I think that's so cool that I'm gonna immediately go install Prettier on my Emacs after I'm done making this video.